here for the second video in 8.2. We will look at the trig functions, now even defining them like a typical function, and we're going to see the graphs. So we're going to go through each of the 6 trig functions, talk about them a little bit, and graph each one so that we get an idea just of how they behave when we think of them as functions, and that will lend itself well to how we're going to use these in future sections where we're taking derivatives and antiderivatives of the trig functions. So let's start with the first one. We're going to call it f of x equals the sine of x. And one thing we want to point out here, as soon as we start thinking of the trig functions like sine of x, with the variable x always is in radians. We won't ever use degrees when we think of the function, and there's a really good reason for that. That will be more clear when we learn the derivatives in 8.3. Kind of the big difference between degrees and radians, and I said it at the beginning back in 8.1, radians measures literally the linear distance that you move in that circle. So if you were to, think of the rotational distance and think of like wrapping a string and then pulling it out straight, the radians tells you literally how far around that circle you've gone, and that's what we need when we start to do formulas, that are going to involve these functions, and we start doing derivatives. Okay, anyway, let's talk about the function sine of x. So we did the sine of different radian values, and we realized, x doesn't have to be limited to between 0 and pi over 2 radians. We can actually go further into, go beyond pi over 2 into the second quadrant, into the third, fourth, right? We can pick any value of radians there. Okay, you get it. So let's look at the graph. So we're going to kind of lay out an xy plane this way. So you've noticed on the x-axis, I've marked, after the origin, I've marked pi over 2, pi, that would be 3 pi over 2, 2 pi, 5 pi over 2, and 3 pi, and then back at negative pi over 2 and negative pi. That's going to give us a good idea of what this function, how it behaves. And you notice, yep, we're going beyond 2 pi, right? And we're going to see some negative values of pi. On the y-axis, we note positive 1 and negative 1. So it turns out the domain for sine x is the entire number line, negative infinity to infinity. But the range of sine x is only between negative 1 and positive 1. It's only going to stick between these two values. And if you don't agree, you're welcome to, take a look at, just punch some values into a calculator would be one way to say, oh yeah, whenever I take the sine of anything, it's always a number somewhere between negative 1 and positive 1. And we can make sense of that with the right triangle as well in the original definition with the ratios. But okay, at the end of the day, that's what we need to know. So let's just, where would be some possible points? And what would this graph look like? It turns out the sine of 0 radians is 0. If we were in class, I would invite you guys to grab your calculator and just type in sine of 0 radians, and it would tell you, yep, that's 0. We can make sense of that with the triangle as well. The sine of pi over 2 radians turns out to be exactly 1. So I'm going to put a dot there. The sine of pi radians goes back to 0. The sine of 3 pi over 2 radians is negative 1. And the sine of 2 pi is back to 0. And so if we draw that, it's got this, gentle curve, comes up to the peak. And my drawing's not perfect, but it kind of comes down like that. And then it's going to keep going this way, round out there, keep going like that. Okay, so that's beginning at 0 and ending at 2 pi, which would be one full rotation around the circle if you were to think rotating. If you were to keep going, this pattern is just going to repeat itself. So we'll have 0 there. The next one's going to be at 1. And the next one after that at 0. And so it's going to start to repeat that cycle again. And it would continue on in the same way. If we go backwards, turns out these points will be there and there. It's going to keep coming down this way, round out, something like that. And of course it will keep continuing on, making that same sort of motion, that same wave again and again and again as we extend out either direction. So it's got this really nice, we call it periodic behavior. So if something, moves according to some kind of a rhythm, where it's cycling back on itself, we can model those things with sine x or cosine of x really, really well. Okay, let's take a look at the next function. F of x equals cosine of x. Again, x is always going to be in radians. I've set up the same XY plane here. If we were in class, I would invite you guys, hey, grab your calculator, make sure you're in radians, put in the sine of 0. Turns out the sine of 0, well, I've already got the dot right there. It's 1. How about the sine of pi over 2? Or excuse me, the cosine of pi over 2. Turns out that would be 0. The cosine of pi is -1. The cosine of 3 pi over 2, and you might have picked up the pattern by now, that's 0. And when we get all the way back around full circle to 2 pi, the cosine of 2 pi is back to +1. So it's got, keep bumping the camera, it's got this same kind of a shape, although it's been shifted a little bit. That's one cycle of cosine, beginning at 1, dipping down, coming back up to 1 by the time we get to 2 pi. And then you can imagine, how it's going to continue. So the next one, it'll come back to 0, and then by 3 pi, it's back down to -1. Try and draw this as smoothly as I can. It's this nice gentle curve. And if we go back in the negative direction, the cosine of -pi over 2 would be 0. And negative pi is back to -1. Of course, it would continue on from there in either direction, kind of in that same cycle. So the cosine of x, maybe you don't want your cycle to begin at 0. Maybe you want it to begin at 1. Depending on what you're modeling. And so you might use cosine of x instead of sine x. Okay, how about tangent of x? So I mentioned back at the beginning, the first video in this section, that we could think of tangent of x as the sine of x divided by the cosine of x. That might help us make sense of the graph. This one I'm going to set up a little bit differently. Quite a bit differently. I'm still indicating pi over 2, pi, 3 pi over 2, and the negatives. But I'm going to stop right there. That will be plenty enough to see in either direction. And I'm not going to note anything on the y-axis. It turns out the domain and range for the tangent of x quite a bit different than sine and cosine, because now we're dividing by the cosine. Some interesting things are going to happen. It's off the screen, but if you look back at your graph for cosine, cosine was 0 at pi over 2 and at negative pi over 2. Well, if cosine is 0 at those values and we're dividing by cosine, there's going to be a vertical asymptote at each of these locations. And that's coming in kind of light on the video, so let me make that a little bit clearer. Vertical asymptotes. Same is true for 3 pi over 2 and negative 3 pi over 2, but I'll save that for now. Let's focus here. We've got a vertical asymptote at positive and negative pi over 2. So it turns out the tangent of 0 radians is 0. And as we move positive, it's going to have this behavior. So it's going to shoot up against that vertical asymptote like so. And coming back the other way, same idea. We could look closely at values for sine and cosine and make sense of this. But at the end of the day, that's what the tangent of x is doing. It turns out the tangent of x, that's its period, that's its cycle. It's going to repeat this shape again and again in both directions. So when we look to the next one, okay, there's another vertical asymptote here at 3 pi over 2. At pi, it will be at 0. And then it's going to have this sort of shape again. Just going to repeat that shape over and over. Same thing back over here. Vertical asymptote will go through 0 at negative pi, and then it's going to have exactly that shape again. There's the graph of tangent of x. So you notice, if you thought about the domain, you're skipping all of these, places where it's got a vertical asymptote. So those values would not be in the domain. But the range is the entire y-axis, everything. So, yep, there's your graph of tangent x. I think we're going to stop this video here. We'll look at the next 3 graphs in the next one.